The kidney has the ability to regulate itself. The amount of blood flowing into the glomerulus is very important. If too much blood flows into the glomerulus, then the glomerulus will become damaged. The GFR, or glomerular filtration rate, must be kept at a specific level. It cannot be too high or too low. If the GFR is too high, the afferent arteriole constricts. This reduces the amount of blood entering the glomerulus. Less blood flows into the glomerulus. As a result, the GFR goes down and returns to normal. If the afferent arteriole fails to constrict, then too much blood flows into the glomerulus and too much blood is filtered through the glomerulus. So the rate of GFR is pretty high, and the tubular fluid travels very quickly through the entire renal tubule until it arrives at the DCT. At the DCT, as you can see here, the DCT is connected to the afferent arteriole. It actually touches the afferent arteriole. The DCT is lined by a bunch of cells that together make up the macula densa. They're called the macula densa. These cells have the ability to sense the fluid going through the DCT, and they also send a message, a chemical message, to the afferent arteriole. So once the afferent arteriole gets the message that it has been sleeping on the job, the afferent arteriole then constricts and the GFR becomes reduced. Less blood will now flow into the glomerulus. So let's go through this one more time. The afferent arteriole fails to constrict, so the GFR is very high. The renal fluid, the tubular fluid, moves rapidly through the renal tubules and until it reaches the DCT. At the DCT, the macula densa senses that something is wrong and sends a message to the afferent arteriole. And the afferent arteriole responds by vasoconstriction. This reduces the GFR. The kidney has the ability to regulate blood pressure. When blood pressure goes down, the kidney releases a hormone called renin. So that's the kidney there. And it releases a hormone called renin. Renin is released into the blood supply. The liver, in the meantime, releases another hormone called angiotensinogen. Angiotensinogen by itself cannot raise the blood pressure, but it must be converted to angiotensin II. The renin helps angiotensinogen to be converted to angiotensin I. Angiotensin I is not ready yet. We need the lungs to release yet another chemical, in this case an enzyme, that will convert angiotensin I to angiotensin II. So here are the lungs releasing ACE. ACE is short for angiotensin converting enzyme. The ACE can now convert angiotensin I to angiotensin II. And angiotensin II has the ability to raise blood pressure. Angiotensin II raises blood pressure in three ways. It acts on the hypothalamus, and in the hypothalamus it acts on the thirst center. It promotes thirst and drinking of water. This in turn increases blood volume. When blood volume goes up, blood pressure also goes up. Angiotensin II acts on arterioles and causes vasoconstriction. As we know, vasoconstriction increases peripheral resistance. When peripheral resistance goes up, blood pressure also goes up. The angiotensin acts on the adrenal cortex and stimulates it to release aldosterone. Aldosterone is a hormone that acts on sodium-potassium balance. It causes the kidneys to retain sodium and water. When that happens, the blood volume goes up. And we all know that the blood volume goes up, blood pressure goes up as well. So in all three cases, blood volume, peripheral resistance, and blood volume again, they increase blood pressure. In this way, the angiotensin II raises blood pressure.